It's my great privilege to introduce our distinguished speaker, Professor Paul. Professor Paul J. Steinhardt is an Albert Einstein Professor in Science at Princeton University and a visionary theoretical physicist who has fundamentally reshaped two distinct fields of science, cosmology and condensed matter physics. As one of the original architects of new creation, he helped establish the standard model of the early universe and later proposed the revolutionary bouncing model of cosmology. This bold paradigm posits that the universe undergoes eternal cycles of expansion and contraction driven by the brane collision in higher dimensions, offering a mathematically consistent alternative to the Big Bang that resolves the predictive paradoxes of the multiverse. Steinhardt is equally renowned for redefining the concept of the matter through his discovery of quasicrystals, ordered materials with forbidden symmetries previously thought impossible by the laws of crystallography. His scientific tenacity led him to organize a daring expedition to the Russian tundra, which he proved the natural existence of these exotic structures in ancient meteorites. A recipient of Dirac Medal and the Oliver E. Buckley Prize, Steinhardt's work stands as a testament to scientific rigor, bridging the gap between the abstract geometry of the cosmos and the tangible atomic structure of the solids. With this, I would like to invite Professor Paul to begin his lecture.
Well, thank you for having me this evening, and I appreciate the opportunity to participate in this voyage through the cosmos. So, the title of my talk today suggests that it's time to take the Big Bang out of the Big Bang theory. The first thing that many of you might be asking yourself is, how is this possible? Isn't there an overwhelming amount of evidence for the Big Bang theory? The answer is yes and no. And the reason is because there's really two ideas involved in the Big Bang theory. One of the ideas is that the universe was once hotter and denser than it is today, and that it's been expanding and cooling and spreading out over the last 13.8 billion years. For that idea, there really is an overwhelming amount of astrophysical evidence, and one doesn't really want to fool around with that story given all that evidence. But the second idea of the Big Bang Theory is that the universe sprang from nothing, began from nothing, had a definite beginning 13.8 billion years ago in what we call the Big Bang. And for that, there is no evidence, not a shred of evidence, because to get to that idea, you have to extrapolate equations back in time by more than 70 orders of magnitude in density beyond what we can test, either in the cosmos or in the laboratory. So if there's not a shred of evidence for it, it's perfectly reasonable to question whether or not it's time to take the Big Bang out of the Big Bang theory. But why? Why should we be doing that? Well, the problem is that if you introduce the Big Bang, it creates a series of problems. The first is the Big Bang itself is a singularity of the equations that we're extrapolating backwards in time. A singularity means a mathematical pathology, a sickness. We extrapolate the equations back and we find that certain moment in time, 13.8 billion years ago, the equations tell us temperatures and densities became unphysically large, infinite. That's impossible. That's an idea that needs to be replaced. So normally when we encounter singularities in solving physical equations of physics, what that usually means is your theory needs an improvement. You're not supposed to take the singularity seriously. The second problem that it creates is a tremendous amount of disorder. This is an artist's conception of what a Big Bang might be like. Um, After the Big Bang, the universe immediately passes through a period in which quantum gravity effects become large. And anything that couples to gravity, anything that's connected by gravity, which is everything, matter, radiation, and space-time itself, is going to undergo huge fluctuations, huge variations across space, creating a lot of disorder or entropy in the universe. In fact, bringing the entropy to the maximum, close to the maximum that's possibly allowed in the universe. But the entropy in the universe today is much less than that entropy. So the puzzle is, how do we go from the large entropy coming out of the Big Bang to the modest entropy we have in the universe today? That would seem to require violating the second law of thermodynamics. And then this entropy takes the form of disordering everything. It makes for a chaotic universe with chaotic inhomogeneity, anisotropy, and curvature variations, as this artist is trying to convey. And that looks nothing like the universe we observe, the early universe we observe. For example, when we look at the last scattering surface from which the cosmic microwave background radiation emanates, and from which we obtain an image of what the distribution of matter was at that time. It shows a very homogeneous, isotropic, flat universe with low, modest entropy. Well, we've known about these problems of the Big Bang for many decades, and this was what motivated the idea of putting a patch in the theory, in the Big Bang theory, the patch that we call inflation, a patch that we place between the Big Bang and, say, the microwave background, the last scattering surface when the microwave background is emitted, to try to correct the problems created by the Big Bang. But what we've learned over the decades since inflation was introduced in the 1980s is that inflation does not help. First of all, it doesn't eliminate the singularity. If some of you have been reading articles or magazines lately, popular magazines, this statement may confuse you because some in the inflation community have decided to rename or redefine what a Big Bang means. Instead of what they propose is to use the word Big Bang not for the beginning, but for when the universe first reheats after inflation. If you use the term Big Bang in this new way to represent the universe after reheating, that's not a singularity. But but by relabeling things that way, it hides the fact that if you go before the reheating and you go before inflation and you extrapolate back in time, once again you end up at a singularity. This theory still has the singularity. It's just sitting there behind the inflationary period. So inflation doesn't help get rid of the singularity problem. Furthermore, inflation makes the entropy problem exponentially worse than it was in the original Big Bang theory. I said that the problem of entropy is that coming out of the Big Bang, we should get an entropy which is much bigger than the entropy we have today, which is a problem. But inflation requires an exponentially smaller entropy to get started. So it exacerbates the problem, makes it much worse. We have to, within a fraction of a second, go from come out of the singularity, create this tremendous entropy, and reduce it by an exponential factor, something like 10 to the Google power, 10 to the 10 to the 100th power, in order for inflation to start. And we have no mechanism for doing that. Thirdly, although it was supposed to solve the homogeneity, isotropy, and flatness problems, as we'll talk about today, it really doesn't. And I should point out that these conclusions don't depend on the particular shape of the inflaton potential, if you're familiar with that idea. It doesn't depend upon whether it's power law inflation, plateau inflation, or multi-field models. They all have these same diseases. And then there's the specter of the multiverse that makes matters much worse. Because in the multiverse, all things are possible. And our particular universe is therefore improbable because there are many other possibilities that can emerge in a multiverse, and they all do, every single one of them, and for an infinite number of times. At this point, some tried to bring in the idea of anthropic reasoning to help sort out the problem of unpredictability of the multiverse. But that doesn't help because although the anthropic reasoning would eliminate possibilities which are inconsistent with our existence, it still leaves an infinite continuum of possibilities which are consistent with our existence, but which are not like us. And furthermore, anthropic reasoning takes us beyond the boundary of scientific reasoning, so that's another reason why I don't tend to recommend it. And then finally, contrary to common claims you might find in the literature, inflation is probably incompatible with quantum gravity. Well, what can we do about this? Well, how about replacing the Big Bang, jettisoning it from the Big Bang theory, and replacing it with a bounce? And by a bounce, I mean a smooth transition, a smooth non-singular transition from a period of contraction to a period of expansion. And by smooth, I mean we do not go through a crunch, we do not go through a phase of quantum gravity generation. This is a smooth transition, non-singular transition governed by predictable equations. In such a situation, you solve the singularity problem because you never have a situation where the temperature and density become infinite. You truly solve the problem. Secondly, you solve the entropy problem because you don't produce the large entropy of going through a phase where quantum gravity dominates. You have no such phase. You solve the homogeneity, isotropy, and flatness problem through a novel mechanism that I will be describing, something that's curiously different from what we imagined in the case of inflation. You avoid the multiverse because the multiverse is a product of having inflation plus quantum mechanics. Well, we have quantum mechanics, but we don't have inflation. So no multiverse, no uncertainty, no infinity of possibilities produced in the bouncing model. There's one possibility, and it's one that agrees with the universe that we observe. Um, there are so-called geodesic incompleteness theorems, theorems like those originally introduced by Hawking and Penrose, which are sometimes these days called no-bounce theorems. But the kinds of bouncing models I'm talking about evade those theorems. Another interesting byproduct of bouncing models is they do not predict what are called primordial tensor modes, which produce a polarization pattern in the cosmic microwave background called B modes. And the reason why that's important, that it does not predict them, is that we don't see them so far. And then finally, this is compatible with string theory and quantum gravity. So many of the problems we saw for the inflationary outcome, Big Bang inflationary idea, are circumvented once you introduce the bounce. Now, as you might guess from this list, this is a huge topic. I can't discuss all this topic in 45 minutes. So I'm going to focus on just one of them, which I think is the most important challenge for any cosmological theory that you might imagine. And that's to explain what we observe from our mapping of the temperature variations across the sky, across what we call the last scattering surface, using based on measurements of the cosmic microwave background radiation. So this is a surface which is a surface in space-time which is beyond the galaxies and taking us back in time about 13.8 billion years. And it shows an image which shows the variation in temperature across that surface. It's false color. So they're showing regions which are hotter or cooler than average. But it's important for this discussion today to keep in mind that these variations in temperature are extremely tiny. 1 part in 10 to the fourth, or 1 part in 10 to the fifth, or even smaller in some places in the sky. So if we just change the resolution a little bit, what we observe is something really amazing, which is across the last scattering surface, across the universe at that time, we were in a state of low entropy, homogeneous, extremely isotropic, the same in all directions, the same in every place across the map, spatially flat. And these are all conditions that need an explanation because they're not what you'd expect coming out of a Big Bang. So we're going to be talking today about two ideas that are designed to try to solve this puzzle of how we get from the Big Bang to the remarkably homogeneous and smooth universe we observe in the microwave background. One will be the idea of inflation following a Big Bang, and the other will be the idea of slow contraction followed by a bounce. Both of them have things in common, which I'll name first, and then we'll talk about the differences. So both of them are described by Einstein's theory of general relativity, which in the case of a smooth universe reduces to the simple equation I'm showing in blue on this slide. It's known as the Friedmann equation. H here represents what we call the Hubble parameter, which measures the rate of expansion of the universe. And the terms on the right represent contributions that will, through gravity, affect that expansion rate. The first term would be the term which describes the energy density, which is going to be causing the smoothing, which would be the energy that's driving inflation or the energy that's driving slow contraction. The second term is the term that describes the curvature of the universe, how curved space is. And the third term is what describes how anisotropic the universe is. That is to say, how different it might be in different directions. The goal of inflation and slow contraction, in either case, is to make sure that the energy density, the first term, becomes large compared to the other two terms, so that the other two terms have a negligible effect on the expansion of the universe, consistent with what we observe in the cosmic microwave background. And they both adopt a strategy of making sure that that first term becomes large compared to the other two. Each of these quantities depends on A, which is the scale factor, which describes the expansion or contraction of the universe. So A grows if you're expanding, shrinks if you're contracting. And all of them have in the case of expansion, all of them have the property that as A grows, if you're expanding, as A grows, all of them are decreasing. But they're decreasing with different powers of the scale factor. So they're decreasing at different rates. In the case of inflation, in an expanding universe, in the case of inflation, when A is growing, we want the first term to decrease, but decrease more slowly than the other two. For that, it's sufficient if epsilon, which is the quantity in the exponent there, is less than 1. Epsilon represents what we call the equation of state. It depends on the ratio of the pressure to the energy density of the energy that's driving, in this case, inflation. So we want to make sure that epsilon is less than 1 because then, although the energy density decreases, it decreases at a power which is less than that for the scalar curvature and less than that for the anisotropy. So over time, for sufficient expansion, the curvature and anisotropy become irrelevant. For slow contraction, there's a similar strategy. However, now the scale factor is decreasing because the universe is contracting during slow contraction. Once again, we want the first term to become larger than the second and third terms. This time, because A is decreasing, all the terms are growing instead of shrinking. As the universe contracts, the energy density, the curvature, and the anisotropy all grow, but they grow at different rates. And if epsilon is greater than 3, in this case, then the energy density, the first term, the energy density that's driving slow contraction grows faster than the second and third terms. So once again, we get a condition where we suppress the curvature and the anisotropy. Now, how do we actually get this epsilon? Well, that depends on the form of energy which is driving the inflation or slow contraction. And here again, the two ideas have a lot in common. They both rely on, in the simplest cases, they both rely on a theory which contains a mixture of gravity, the first term in the action in the top line, a scalar field, which has a kinetic energy, which is the second term, and it also has a potential energy, which is the third term. Because they share the same action, they satisfy the same equation of motion, which describes how the field changes with time. And that's the equation in red below. The difference in the two theories is number one, in the case of inflation, the universe is expanding, which means that the Hubble parameter, which describes the expansion, is positive. And the middle term in that red equation acts like a kind of friction term for the field, transferring energy from the field into gravitational energy. In the case of slow contraction, the universe is contracting, so H has the opposite sign, a negative sign. So instead of acting like a form of friction, it acts as a form of anti-friction on the field. It converts gravitational energy into pushing the field ever faster. And that energy buildup ends up turning into the matter and radiation after the bounce that forms the matter and radiation we see in the universe today. The second way they differ from one another is the particular details about the potential. In the case of inflation, we want to have a potential which is large and positive during the period of inflation. That's because we want epsilon to be less than 1. And epsilon for a scalar field is given in that equation in blue. It's the ratio of 3 times the kinetic energy over the total energy. So kinetic over kinetic plus potential. If we want to make epsilon less than 1, we're interested in making the kinetic energy small. The smaller the kinetic energy, or the slower the field is changing its value, the smaller epsilon is. So for example, in this particular example, and there are many examples of potentials of different shapes which are possible, but in this particular example, what we want is the field in somewhere, let's say on this plateau, where it's changing because the potential energy is very flat, the field changes very, very slowly. And so if it starts at rest, it will change very, very slowly. That'll produce the condition we want of small kinetic energy compared to potential. That'll produce the condition of epsilon less than 1. And if its epsilon is less than 1, the scale factor grows as a power of time that goes with a power 1 over epsilon. So it grows with a very large power of time, which is what we mean by accelerated expansion. Okay, how do we get contraction? Well, if we have a universe which is slow contraction, I mean, if we have a universe which is contracting, one also can use a scalar field and a potential, but in this case, the condition we want is different. We want to have epsilon large, not epsilon small. But that's easy to accomplish. All you need is for the potential to be negative. It doesn't really depend on the shape or exactly where you're on the potential. The moment the potential is negative, which is very possible in quantum field theories or very easy to achieve theoretically, in fact, very natural to achieve theoretically. If the moment you have that, you automatically have the condition you want, epsilon greater than 3, and it's not hard to make epsilon large. It could be 10 or 100 or 1,000, which means the contraction becomes extraordinarily slow because the contraction occurs, well, we can choose our time coordinate so that contraction means time is negative but moving towards 0, where 0 would be where we'd have the bounce. As t is getting smaller, the scale factor shrinks as t to the power 1 upon epsilon. And if epsilon is big, that means we're slow. And the bigger it is, the slower it is. Okay, so these are things that the two have in common. They both depend on potentials, although the details of what we need for the potentials are different. They're both essentially equally attainable. Now let's get to the question, the key question. How do we smooth the universe? How does the universe become smooth and flat? Well, let me have you imagine a moment, for those of you that are already familiar with inflation, have you imagine that a high school student comes up to you when you're both stepping into an elevator, and ask you to explain how it is that inflation solves the smoothness and flatness problems. The student doesn't know any equations, doesn't even know the Friedman equation I wrote down, but wants an explanation. Try to imagine for a moment what you would tell that student when you only have a brief elevator ride to explain it. I imagine most of you would ask the student to picture the following thing. Imagine space-time is like a sheet, which is curvy and wrinkled and distorted after coming out of the Big Bang. And that what happens is that when inflation aspect begins, what it does is it stretches that sheet so that it becomes smooth and flat over the scale that we observe it. If that's the idea you had in mind, some version of that, sometimes people describe a wrinkly ball or other metaphors, but if this is the kind of idea you have in mind, it's no wonder. It's a very simple idea. It's very intuitive, very easy to learn. It's a very simple idea, very easy to remember. It really, it's hard to get out of your mind as an explanation, and it's easy to teach. So it's no wonder that this idea carries forward. It's one of the things that convinces people that inflation works. The only problem with this idea, despite all its nice properties, is that it happens to be wrong. It doesn't represent general relativity or how inflation works correctly. And it's misleading because it suggests that the only way that you can smooth the universe and flatten the universe is by expansion. And I'm about to show you the opposite is the case. Slow contraction is a powerful method, in fact, a more powerful method of smoothing and flattening the universe. You can tell that something's wrong with this explanation if you think a little bit and realize that I never mentioned in the explanation that the expansion was accelerating. The explanation only depended upon the universe expanding. It didn't depend upon the rate. But in fact, it's very important what the rate is, because when you actually solve the full equations of general relativity, if the universe is decelerating rather than accelerating, the wrinkles grow. They carry their own gravitational fields in general relativity, and the conditions in which the universe is not accelerating but decelerating, that gravitational effect causes the wrinkles and curves and warps to grow rather than to shrink. Um, and um, and in fact, there's been a lot of expansion since the Big Bang. We depend on this effect, in fact, to make the structure in the universe. In the microwave background, we only have tiny little wrinkles in the distribution of matter and energy, but the universe is decelerating in its expansion, and it's that deceleration that causes those wrinkles to grow and become concentrated enough to form all the lumpy structure we observe in the universe today, including planets, stars, galaxies, and clusters of galaxies. So it's not true that simply by stretching the universe or simply by expanding the universe, you can smooth it. But then, as I also say, in order to, the other reason why this idea is misleading is because it also makes it seem like it would not be possible to smooth the universe by contraction. But we'll see, as I said, that the opposite is the case. Now, one of the challenges to understanding exactly how you smooth is that if you begin with a universe which is not smooth and try to solve the equations of general relativity, they find that they're too complicated. We can't, with pencil and paper, solve those equations and test whether or not this universe smooths or not. But these days, we do have another set of tools available to us that weren't available to us back in the 1980s when inflation was invented. These are the tools of numerical general relativity, solving the Einstein equations on a computer. When inflation was first invented, already theorists were trying to develop tools of numerical general relativity, but there were all kinds of challenges, and it took 35 years before those tools could be developed. And they were first applied to describe the in-spiral and merger of two black holes and the production of gravitational waves, a set of calculations that were crucial for the famous LIGO experiments that first detected gravitational waves coming from the merger of black holes. But in recent years, a group of us, or several groups, including our group, have begun to adapt the tools of numerical relativity to this fundamental problem of cosmology. What does it take to smooth and flatten the universe? There are a lot, uh, uh, recasting the equations of numerical general relativity for this cosmological problem are non-trivial. You can't simply take the code you use for black holes and apply it for cosmology. So it takes quite a lot of development, literally years of development. You have to, among other ingredients, figure out how you're going to formulate the Einstein equations. There are many ways of expressing the Einstein equations mathematically. You have to find one that's optimal for your purpose. In the examples I'm showing, we're going to be using what are called the tetrad formula, the tetrad formulation, for those of you that know what that means. You also have to choose a gauge, a way of slicing time that fits the problem. So in general relativity, you can, in principle, choose your services of constant time or your slicing of constant time as you wish, and it shouldn't make a difference. That's true theoretically, but computers are sensitive to the time slicing, and some, or actually most choices of time slicing will lead to numerical artifacts, things that look like that will crash the program, even though there's nothing wrong physically, simply because you chose an unfortunate choice of time slicing. So you have to figure out an appropriate time slicing that doesn't have that problem. Then after you've done all that, if you've worked out all that mathematics, which already takes a few years, then you have to work on developing a numerical code that's going to be stable and well adapted. And even when you have a numerical code that's well adapted and running, you then have to find ways in which you can measure the outcome. Well, actually, the starting condition and the outcome. You want to make sure you're starting from conditions that are far from smooth and flat and end up with conditions that are sufficiently close to smooth and flat that it's consistent with what we observe. Just to give you a visual sense of what this involves, I've written in compact form the Einstein equations of general relativity in what's called the tetrad formalism. The quantities where you see the capital E's, those are the so-called tetrads that describe space-time. There's a quantity called the lapse. There's a quantity K, which represents the curvature. There's a term sigma. That's going to be an important term that measures the shear or anisotropy caused in space-time in general relativity, and so on and so on. So lots of complicated equations that have to be solved. Horrible, nonlinear, coupled partial differential equations. Then, to add to the challenge, you have to solve in parallel what's an equation for the lapse, which describes the time advance or delay on your surfaces of constant time. And that satisfies a different kind of partial differential equation called an elliptic equation. And one of the hardest things to do in numerical or computational physics is to solve a problem that combines hyperbolic equations like the ones on the left with an elliptic equation like the one on the right. That makes a particularly nasty challenge, which also you have to overcome. And then general relativity has another nasty feature to it, which is you can solve these equations using nonsense initial conditions, conditions that that general relativity doesn't allow because it violates one of the conservation laws. So you also have to check along the way that you're satisfying the conservation laws at each step to make sure that you're solving equations that are actually meaningful. So imagine that this whole process takes, maybe 4 or 5 years to develop. And finally, you get to the point where everything is working and you're ready to show the results of a simulation. So I'm going to now show you some results. So imagine you have a box in which you started off with wild initial conditions. You then either have inflation or you have slow contraction, and you're going to try to follow and see if it manages to smooth the universe. it, you're solving the full Einstein equations. Um, for your initial conditions, you want to try to choose initial conditions that are far from smooth and flat. Well, in the simulations I'll be showing, I'll be only showing you tracking the conditions in a particular slice through the simulation. It really doesn't make a difference which slice you choose. They're qualitatively the same. And along each slice, I'm going to be representing a slice with three surfaces. One which represents the distribution of energy in the field that's driving the inflation or driving the slow contraction. And I'm going to call that combination omega phi. That represents the fractional contribution to the expansion due to the scalar or expansion or contraction due to the scalar field. Then we have the red curve, which represents the distribution of spatial curvature, and the green one, which represents the shear. A universe which is shearless and curvatureless would be one which only had blue at the top and none of all the other two colors at the bottom. But you see, we're beginning very far from that initial condition. We're beginning with the green, which is the shear, the anisotropy, much higher up, which means there's much more shear than there is anything else in this particular example. It's just one example, but that's the first example we're going to look at. And we're going to now ask, now that we run the equations and we try to introduce and we have our smoothing component, what happens to the shear, curvature, and scalar field? So here goes the simulation after the 4 to 5 years of effort to get to this point. We hit the start button and we're done. Within instants, we're done. The blue, which was near the bottom, is now at the top. The green and red, which represent the curvature and shear, are now at the bottom. This is a universe which now has no curvature and no anisotropy. And it only has a smooth, flat surface, which means it has a homogeneous and isotropic distribution of energy. You saw how fast it went. Let's go. I'm going to show it again. Now you know what to look for. Don't blink. We're done. This is an example of a very powerful smoothing mechanism, which in a matter of instants manages to smooth and flatten the universe. An instance, what would be instants of time in the early universe. What we're looking at in this particular case happens to be not inflation, but the effects of slow contraction. It's a demonstration of the power of slow contraction to smooth the universe. And in this case, I've kind of underestimated the power to make the movie because I chose epsilon to be rather small. The bigger I'd make epsilon, the faster this would go, but then it would be hardly possible for you to see anything at all because within a frame, it would already be smooth. Now, the fact that slow contraction is this powerful in this example is actually puzzling for the following reason. It's an example of what I like to call spooky action at a distance. Many of you may have heard that phrase, spooky action at a distance, when referring to quantum physics. But this is not quantum physics at work. This is general relativity at work, in which quantum physics plays no role. We're solving classical equations of motion. But still, it's a kind of spooky action at a distance because the fact that we're able to smooth the system this way is surprising given what we thought we learned from the case of inflation. Inflation, we learned that in order to smooth the universe, we first of all have to make the universe smooth on scales when the different regions in space, you have to make it smooth over a region which is smaller than a Hubble radius, over the scale of the causal horizon, because we can only make the universe smooth if different points are in causal contact with one another. And then inflation comes along and stretches that reason. But in this case, the universe is contracting. And the horizon when we begin, is roughly the size of this ring over here compared to the box, compared to the surface. And the universe is contracting. So the ring is going to be shrinking. The Hubble horizon is going to be shrinking. So you might have expected that you can smooth the universe on the scale of this ring, but you couldn't smooth the entire box because the entire box includes regions which are much farther apart than the diameter of that ring. You should have only been able to sort of smooth maybe a patch of it. And yet what we've seen is the entire box, both within the ring and well beyond, smooth. So what's going on? What's going on is something quite magical that's associated with contracted universes, but not with expanding universes. And it's a quality that we call ultralocality. So if you've learned the word inflation in your study of cosmology up to this point, here is another important word to learn for the future, ultralocality. It's an idea that was first developed or first invented in the 1960s and 70s by Belinsky, Kalatnikov, and Lifshitz, who began to study the effects of contraction on general relativity. And what they showed is something very surprising, which is that as the universe in a contracting universe, all the terms in the Einstein equations, which involve what we call spatial gradients, terms that tell you something about the difference between 2 points in space, which are the terms which allow different points in space to communicate with one another, connect information with one another. All those terms drop exponentially rapidly as the universe contracts. And if that happens, what that means is that the horrible nonlinear partial differential equations that I showed you now turn into ordinary differential equations. That means they have no spatial derivatives in them. And they're the same equations at every point in space. That's an amazing thing. If you want to make the universe smooth and flat, you suddenly, just by contracting, have every point in space, doesn't care about its neighbors. Every point in space will be solving the exact same equations. This idea was first tested uh, in, uh, numerically by the work of this group in the early days of the development of numerical relativity. And only recently, in the last few years, have been tested the case for slow contraction. Here's an example of what I mean. Here's just tracking one of the equations in which one of the equations that I had on that transparency, in which there are terms, the last two terms, which have in them, some of you will recognize a symbol that says partial with respect to I. Those are spatial gradient terms. Those are spatial, that's the symbol for spatial gradient. So those are the terms that BKL said were going to fall away. And the other terms are terms which don't have spatial gradients in them. And what the plot shows is that the terms on the right, the two gradient terms, they're falling off exponentially fast as the universe is smoothing compared to the rest of the terms. So the universe is governed by the ultralocal equations, which have no spatial gradients in them and which are the same everywhere in space. This is a proof that ultralocality occurs. Now, slow contraction is also critical because what BKL showed was that if the universe is undergoing fast contraction, they only considered the case of fast contraction. They only considered the case when the universe is dominated by matter or radiation or simply gravity. Those are cases where epsilon is less than 3. What they showed is that when you solve the equations, yes, every point in space obeys the same equations, but they start with different initial conditions. And the outcome you get when you solve the equations is super sensitive to those initial conditions. They are what we call classically chaotic equations, which means although they're obeying the same equations, the universe evolves very differently in different points in space, so-called chaotic behavior or chaotic mixed master behavior. What they missed was the idea if you have slow contraction, the opposite happens. Now, when you solve the equations, it doesn't make a difference what the initial conditions are. Every point in space not only obeys the same equations, but ends up in the same place. And not just any place, in a universe in a region which is flat, homogeneous, and isotropic, exactly the conditions we want. We've seen that when we ran the simulations on the right with slow contraction. Now we're going to take the exact same initial conditions and not just do the case of slow contraction, which smooths, but the case that BKL considered, which doesn't smooth. So here we see just what I was saying, that BKL sort of missed an opportunity of discovering slow contraction and what I think is a fantastic way of smoothing the universe. And just to emphasize the point, we've run hundreds of simulations with different kinds of initial conditions, even ones with incredibly wild conditions, even wilder than you might expect coming out of the Big Bang. And nevertheless, with essentially the same amount of time, slow contraction is able to turn that into a smooth and flat universe. And here's another way of representing it. This is a way in which this is what we call a shear map. Sigma here represents the shear, and a universe which is smooth and flat is going to be a universe which has no shear. So it's going to correspond to the origin in the lower right-hand corner. Each one of these threads here represents tracking a particular point in our simulation, where the red represents where we start, and then the thread shows you how you evolve, how the shear evolves. The quarter circle represents the boundary between regions which are close to smooth and flat, close to the origin, from regions which are significantly far beyond the smooth and flat, as you might expect after a Big Bang. So notice that all the red dots are at or way or beyond, or some of them way beyond what you'd smooth and flat, the kind of wild conditions you'd expect after a Big Bang. But due to the slow contraction, all those threads end up making their way to the origin along different paths, but solving the exact same equation, they manage to reach the same final point and find it quickly. Now, what about inflation? Now you should be concerned because what we've seen is that ultralocality plus slow contraction are powerful ways of smoothing the universe. But between the Big Bang and before inflation can start, instead of slow contraction, we have slow expansion. And if slow contraction smooths, causes ultralocality and smooths, slow expansion is going to cause anti-ultralocality and cause unsmoothing. Uh-oh, now we have a problem that we can't just ignore those curvatures in space-time, like you were supposing in the stretched sheet analogy. Those um, those variations can actually fight against the contraction by growing rather than shrinking. So for slow contraction, we saw that even wild variations are able to smooth. But now look at the inflation example where we've begun something much wilder, much milder, very gentle variations. And yet, because to get from the Big Bang to inflation, what happens is, yeah, just the nightmare scenario we expected. We find things grow, and this interferes with the inflaton managing to take over the universe. As illustrated here, on the left, we see the example of the threads that I showed you before for the slow contraction. On the right, we see the example of the threads, what I've shown you for inflation. Notice the red dots are already inside the circle, so are already pretty close to flat, smooth, smooth and flat to start with. We've given inflation a head start. But even then, the threads do not make it to the origin. The universe does not smooth. So, I said at the outset, the 4MS challenge for any cosmological theory is to explain the low entropy, homogeneity, isotropy, and spatial flatness of the universe. What we have seen is that inflation fails to meet this challenge, and slow contraction does. In particular, what inflation requires in order to get started is an extraordinarily low entropy, much smaller than the entropy we have today, creating a more serious entropy problem. It requires a universe which is already homogeneous, more homogeneous than what I already showed you in this last simulation. Extremely isotropic, extremely flat, and not just at a particular point, but over a substantial region on scales larger than a causal horizon size before inflation can even start. In other words, the problem of inflation that inflation was intended to solve, the fine-tuned initial conditions required by the original Big Bang model, is what inflation itself requires to begin. This is not progress. We need to solve, we need to, we need to have solved the problem before inflation starts. On the other hand, we've seen that for slow contraction plus a bounce, we solve the singularity problem, we solve the entropy problem, we solve the homogeneity, isotropy, and flatness problems through this beautiful idea of ultralocality and slow contraction. And in doing that, we avoid the multiverse and we evade geodesic completeness theorems. We predict no primordial tensor modes consistent with what we observe, and we are compatible with string theory and quantum gravity. So these are the contrast between inflation and the contrast between Big Bang followed by inflation versus slow contraction and bounce is stark. And I think it's a compelling reason why it's time to take the Big Bang out of the Big Bang theory and give serious consideration to replacing the Big Bang with a bounce. Thank you.
Thank you, Professor, for your brilliant and truly inspiring lecture. I would like to express my sincere gratitude to you for sharing such profound insights and for enriching us with your perspectives. Thank you once again.
Well,
Uh,
thank you. Thank you for your
okay.
attention.
Yeah. The first question is by Mr. Srinjay Paul from the University of Kalyani. He's asking that is time travel in microscale not possible as to achieve the negative entropy locally? There will be a massive influx of entropy from the global perspective to make the overall entropy increase.
I'm not quite sure what the question's referring to. I think the question might mean, can one have fluctuations in entropy, which are downward fluctuations in entropy? So, for example, could inflation start by some rare fluctuation in some rare region of space, in which the entropy, instead of being what you'd expect after the Big Bang, is the very low entropy you need for inflation to begin? Yes, that's a physical possibility, but it is exponentially unlikely because the difference in entropy is something like 10 to the Google power. So that means the probability is 10 to the 10 to the Google power of producing such a region. And much more likely than that is to produce a region which is smooth and flat without any inflation. So it's actually not, it doesn't help. That possibility is not a good solution to the problem.
Okay. Okay, so we'll take a next question. Okay. This is by Professor Tejendra Singh from the Tata Institute of Fundamental Research. So he's asking that what decides the energy scale at which the bounds take place? Can this scale be as low as 1
Um,
TeV? Yeah, yes.
yes, I think in principle, in terms of just smoothing and flattening the universe, it can be as low as 1 TeV. It can't be much lower because then it would begin to interfere with processes that we have a lot of begin to interfere with um, um, successes of the Big Bang theory, which we don't want to mess up, like the production of the light elements. But TeV is still high enough that the theory would still be consistent. I should
Uh,
make one other point. Let me just add one other point about that. So
yes,
in
yes.
the bouncing picture, the universe never reaches infinite temperature. It never even reaches the Planck temperature where quantum gravity becomes important. The universe uh, has a limiting upper bound in its temperature, which is well below the scale at which quantum gravity effects are important.
Yeah. Next question. So this question is by Mr. Kumar Ravi from Swami Vivekananda University, West Bengal. So suppose one postulates that no physical entity in the universe, including the universe itself, can attain a density greater than that of an atomic nucleus. In that framework, singularities such as those associated with black holes and the Big Bang are excluded. Can this hypothesis be ruled out by current cosmological or astronomical observations, such as the cosmic microwave background or others?
I'd say the problem is we know no reason why there should be this limit. But if there is such a limit, we don't know how to evolve out of it. So if you create a sing, if you're once you begin with this high density, um, uh, you begin with such a large concentration of matter, the gravitational attraction of that matter will resist expansion even more than those wrinkles I was showing you in space-time. So we don't know how to formulate such a theory.
Yeah, thank you, sir. So we'll move to the next question. Next question is by Mr. Rajat.
Hmm.
How How replacing Big Bang with a bound solve entropy problem?
Okay, there are several aspects to this. The first is you never go through the quantum gravity dominated era that caused the entropy problem after a Big Bang. So the big problem you have is that you have a singularity, and just after in the Big Bang theory, and just after the singularity, the universe goes through a phase of quantum gravity domination, which quantum gravity fluctuations produce this very large entropy. And that doesn't occur in the model at all. Furthermore, as you contract the universe becomes more and more homogeneous and smooth. At least the part of the universe on the scales we observe become smooth and uniform and very low entropy. So by the time you bounce, you're at a state of actually very low entropy. Then you convert the energy that's in what was in the slow contraction field into matter and radiation, but that's only a modest amount of entropy consistent with what we observe.
Okay, sir.
For
Thank
the
you.
question.
Okay. So we'll move to the next question from the College of Burdwan Raj College. So the question is like, is the entropy of our universe is always increasing at every point of the universe?
No, the total entropy within the universe is increasing. And by the total, I mean both the parts we can see and the parts that we can't see that are beyond beyond what we can observe from where we can observe light or with which we can have causal contact today. The total entropy is increasing. That's the second law of thermodynamics. But you can, especially as structure forms, have regions where the universe becomes more ordered and but somewhere else there must be sufficient disorder so that the total, sorry, entropy is increasing, consistent with the second law. So there's no violation of second law happening in the universe on the whole.
Okay, so let's move to the next question by Ms. Pragya from IIT Kanpur. She's asking that, is it possible that a black hole was once a galaxy that expanded and later contracted into a singularity?
Um, it's this is conceivable, but it's we don't know of an example that we've observed in the universe that would correspond to this case. But there's nothing that forbids such a thing.
Okay,
Instead, what we see is the early universe has black holes surrounded by matter which form galaxies around them. There's a relationship that most galaxies, for example, our own Milky Way, have large black holes at their centers, but there hasn't been time for it to consume the galaxy, which is what I think the questioner is asking. Thanks.
okay, let's move to the next question. Okay, the question is from Mr. Dept, PRSNC College, Kolkata. So he's asking that matter and antimatter should have been produced equally, yet we observe a strong matter antimatter asymmetry. Why is there more matter than antimatter?
Again, thanks for the question. So this is the assumption that matter and matter should have been produced equally is the is the weak point of this argument. That depends on there having been a symmetry in the laws of physics between matter production and destruction and antimatter destruction and production. And that was an idea we had back, let's say, in the early 60s. But already by the early 70s, we realized that that there does not have to be such a matter and antimatter symmetry in fundamental physics. In fact, we have very strong reasons to believe there is no such thing. And because of that, because it's possible to have what we call baryon number violation or an asymmetry between matter and antimatter, you can generate that asymmetry that we observe dynamically. There's, in fact, not a unique explanation. There are a handful of different examples which use that idea to generate the observed matter and antimatter asymmetry we observe, and that can be fit within either the Big Bang inflationary paradigm or the slow contraction bouncing paradigm.
Okay, thank you, sir. Let's take a last question. The question is from Ms. Shweta. She from Star Spaces Experience, and she's asking, "Hi, sir. You spoke about ultra locality. My humble and simple question is an ultra local state, different regions of space effectively stop communicating with one another. Paradoxically, you argue this leads to a more uniform universe. Could you explain the intuition behind how less communication between spatial points results in more homogeneity across the entire cosmos by the time of the bounce?"
It's a very perceptive question because you might worry, in fact, that we were taught, we were taught when we were studying inflation, we were taught just what you suggest, that if you were to take points which are not in communication, there's no way to smooth them. But what's missing is the idea of slow contraction. So it's not just that the equations become ultra local, it's that in a background of slow contraction, those equations have what we call an attractor solution, a single outcome, which is special, which every point is drawn to independent of the others. And it happens to be, in the case of slow contraction, one which every point in space in its most immediate surrounding is going to be flat and homogeneous and isotropic, so that when you look at the collection of points, they all end up at the same place. They get there at different times, as I showed you with those threads. They weren't all tracking in parallel to one another. They get there at different times, but they all get there in an overall short period of time. So it's the combination not just of ultra-locality, but add to that slow contraction. It would not be the case, for example, if it were fast contraction, like I showed. But thanks for the great questions.
Thank you, Professor, for addressing these questions with such depth and clarity. So, on behalf of the Bhaktivedanta Institute, I would like to once again express our sincere gratitude to you for sharing your insights and wisdom with us today. Your lecture has given us deep insights into science and our understanding of the universe, and we are truly grateful for your time and generosity. Thank you very much, Professor Paul.
Thank you, and thank you for your attention and the
Thank you.
opportunity.
Thank you. Thank you.
Bye-bye.